Okay, so Geoff Whittle is going to give us his second lecture on matroid theory.
Right. So just picking up where we left off yesterday, the connectivity function of a matroid, just this function is you take values in partitions of the ground set, we can think of it that way, and its value on a particular partition is this calculation here. And remember what that means is if the matroid were represented, if the matroid were a set of points in some vector space, then what I've done is I've taken two disjoint subsets, and this thing here measures the rank of the intersection of the span of those two disjoint subsets. So you've got A, it's got a span, you've got B, it's got a span, and those subspaces will span some set of points. This thing here measures that rank. But there need not, but this is something that makes sense for an arbitrary matroid. Doesn't have to be a representable matroid and anything. And there need not be any elements of the matroid in that intersection. There may or may not be. But it still makes sense to think of that as a measure of the extent to which A and B communicate within the matroid. And if you think about it from a linear algebra point of view, it's just clearly the case. If I find a partition A and B where I can get that value equal to 0, that means that the matroid has skew subsets. I can find skew subsets. And so that's a separation in the matroid. Obviously, skewness is just, there's no communication at all between them. And so that's how, for matroids, that means you can think of the matroid as being the direct sum of two smaller matroids, right? That's what sort of skewness corresponds to. But things that are close to that, that we might have a situation where I can find a partition AB, such that when and again I'll just assume that we're in a vector space to make it clear, that when I look at the span of A and the span of B, they meet in one point. Remember, this is projective geometry, so there's no zero vector kicking around. They meet in one point. That would be a two separation. And we call it a two separation, and we'll see why. That's a place where this thing has value 1, but it's called a two separation. Why not call it a one separation? That's a good question, and we shall see. And in fact, if I find a place where I can partition it so that the spans meet in a line, then that's a three separation, and the terminology is perhaps a little bit strange. So that's we've got low communication if I can find values for which this thing is small. The first thing to observe is so that there is just one notion of matroid connectivity, really. And this is the connectivity function. If you look in the literature, you'll find things like internally four connected or three connected or vertically four connected, literature matroids. But what you're really saying is that all they are saying that you've got blah type connectivity if this function lambda behaves in a certain way. So there really is only one type of connectivity, that function lambda, and there's different ways of labeling connectivity according to how that function lambda behaves. So it's quite connectivity in matroid. There's nothing like in graphs where edge connectivity is significantly different from vertex connectivity. So what does the connectivity correspond to if the matroid's a matroid of a graph? Well, this is a bit of a surprise because why? When we take the matroid of a graph, we throw away the vertices, and then we see, well, okay, now I've got this matroid that I got from the graph. I've thrown away the vertices. I've just got the edges. And I take the connectivity of this thing. Well, I would have expected to have got edge connectivity, right? If it's going to correspond to anything in the graph. But no, it doesn't. It corresponds to vertex connectivity in the graph, which is just one of those little surprises that's deeply satisfying somehow. I don't know why. But, okay, so matroid connectivity generalises vertex connectivity in graphs. And I'm doing a little slight fudge here because I don't want to get bogged down in some technicalities. But if I take a graph and I take a partition of the edges, right, so that's how and then I assume that A and B induce connected subgraphs. Well, this doesn't have to be the case, so I'm just showing you in the case that they do. If they don't induce connected subgraphs, it's subtly different, but it doesn't make an overall difference in what the point is. Then in the matroid, the rank of this set here is the number of vertices in A that A meets minus 1. Why is that? because the rank of the matroid is the size of a maximum spanning tree. It's a connected subgraph, and that means it's got number of vertices -1. Why a spanning tree? Because that's a maximum sized independent set. And the same for B, and the rank of the matroid itself is the cardinality of B -1, assuming that G is connected. And then what that tells me is that lambda in the matroid of AB measures the cardinality of this set here -1. The cardinality of that set there -1. And so this set here is a set of vertices that are incident with both A and B, with edges in both A and B. That will always be a vertex cut. Not necessarily a minimum size vertex cut, but it's always going to be some sort of vertex cut, and that's easy to verify. And so what you're measuring is the size of a vertex cut -1. So in that very elementary example there, we've got, that would be the case where this here was 2, but the actual lambda is 1. So why do we call it a 2 separation when lambda is equal to 1? Because if it came from a graph, we would be measuring, we would be identifying a 2 separation in the graph. And so that's the terminology comes from graph theory. As far as I'm concerned, that's the wrong way around. One should call this a 1 separation in the graph. So I feel that there's been great injustices happened over time, and I'd sort of like to reverse this, but I suspect I'm swimming against the stream there. Okay, so what do we... Here, it's about time we sort of saw some nice theorems, and here is something that I think is particularly attractive. There's a version of Menger's theorem for matroids, but forget about Menger's theorem. Let's just think about matroids, and we'll see later on why it's a version of Menger's theorem. If I take 2 sets in a matroid, two disjoint subsets of edges in a matroid, then this kappa measures the connectivity between A and B. And what's that saying? That's saying, look at all partitions, A prime and B prime, where A prime contains A. Oh, okay, so remember you've got to think of this as, again, think of this as the matroid, some big set of points in some vector space, right? That's what you're looking at. And you've got some sort of subset of A, some subset of B, and there's lots of other points around. And so what you're looking for is the minimum value where you take a partition where A prime contains A, B prime contains B, and you take lambda of those A prime, B prime. So it's saying that when I find that minimum, what's that minimum doing? It's giving me an upper bound for the amount of communication between A and B, right? I can't, once you show me a place where A is on this side and B is on this side and there's stuff there, but there's a small separation, a separation of a certain size, matroidally, separating those two things, then you've bounded the amount of communication. And of course, so you look across it and find the minimum of all of these things, right? So you sort of, in some sense, it's not unlike trying to find a minimum size vertex cut that puts A on one side and B on the other, if you have graphs, but we're trying to find a partition of the edges that has that property. Then Tutt's linking lemma says this, and it might take a little while to digest it, but it's a very simple statement, that you can find a partition xy of the elements that are out of A union B, such that when you delete x and contract y, now you get a minor. You delete these things in x, you contract, and then you get a minor, and the ground set of this minor is A union B. And there exists a partition with the property that when you do that, the lambda value, the connectivity in this minor between A and B, is exactly the original connectivity between A and B in the graph. So what's that saying? What it's saying is, so what are we saying? That I look at A there and B there, and I'm telling you that there's no separation, say 10. The minimum is 10. So for every partition that puts A on that side, B on that side, the lambda value is at least 10. Well, that's saying I can remove all of the stuff. What's removing mean? Deleting, throwing away. Contracting means projecting. So I just sort of, as I project, A and B start moving closer into each other. And I can eventually project and delete until, whoops, I've got only A union B. And the connectivity between A and B is that value. So that tells me that I can actually achieve that amount of communication. Because if I can do it in a minor, all I've done is lost information in taking the minor. If I can find that communication in the minor, I could have found it in the original matrix. So that tells me that this is a good characterization of the amount of communication between A and B. Yeah.
So is that also extreme? I mean, you say here that there exist partitions, but if you take another partitions, you get an inequality. I mean, if you choose to delete or contract the wrong vertices, will you always get?
Oh yeah. Typically, typically if you randomly choose a partition, you'll be done for. Yeah. And the proof is no.
Yes.
So there exists a partition. So
Yeah,
I'm not telling you how to find such a partition.
No. But my question was, if you take another partition, will you get an inequality there?
Is it less than or equal to
Yes.
in general?
Oh, yeah, in general, yeah.
Yes, so-
Because the connectivity function is monotone under minors.
Okay.
So if I take a minor, I can't increase connectivities in a minor, and nor should you. I mean, if you remove an element,
Yes.
how could you increase the connectivity? Yes, actually, I'm glad you asked that question because that was something I meant to mention, but
So
didn't.
you're saying that if you take x prime and y prime, you'll get a greater or equal lambda?
Greater.
on the left?
I'll get it less than or equal to. It's always less than or equal to.
Less than or equal to kappa.
Yes.
Yeah.
So you can write kappa as the maximum of the left-hand side over all x and y.
Oh, yeah.
Yeah, I mean, it's a sort of a min-max theorem, right?
Yeah.
The minimum of this is the maximum of that.
Yes.
Now,
But in that case, why where you're defining kappa of AB, are you saying this minimum? I mean, if you've got this monotonicity property, why do you need to?
Oh yeah, okay, yeah, you're right. That's right. This is already defined as a minimum, but you could restate it's really it's a really min-max type concept. That's what.
now,
And that's what okay. And of course, Menger's theorem is saying that wonderfully, two things sort of end up the minimum is.
but is this precisely the vertex form of Menger's theorem when you specialize the graphs, or is it only an analog?
It's precisely the vertex form of Menger's theorem when you specialise the graphs. And let's have a think about that. And again, there's just there are some small issues related to whether A and B induce subgraphs that are not connected. So but those small issues are easily resolved. So let this be the matroid of a graph, and let A be some set of edges, B be some set of edges. So we can look at the vertices in A and the vertices in B, right? And what's this thing saying? There's a partition xy, so that when I take this minor, I get that connectivity directly. So that means there's a minor where when I find that minor, A and B, the connectivity in that minor between those vertices is K.
Which means they
have K vertices in common, right? They have K vertices in common. When I look at what A and B, the vertices that they induce, then they have K vertices in common. Well, how could I have got that minor? Well, first of all, let's delete the delete edges. Throw them away. I'll find my X and Y. Now look at my contract edges. Well, I'm telling you that if those contract edges don't form K disjoint paths in the graph, you're done for. There's not going to be any cycles, because I could put an edge in a cycle in the delete. It's just that I'll make the delete edges, I'll maximise the number of delete edges.
Internally vertex.
And they better be internally vertex disjoint. I've just given you a version of Menger's theorem, which is equivalent, under transformations to any version that you want, really. And that's a corollary. And by the way, this has got a very easy proof. All you do is you sort of just get the axiomatics of the rank function and stuff like that, and you say, I'll have a go. I'll look at an element and I'll say, oh, is this a delete element? And you have a go at deleting it, and you know, oh no, the connectivity's gone down. Well, if you know the connectivity goes down when you delete it, that tells you it won't go down when you contract it. And that's a four-line proof. But I'm not going to do it. But
Is there any matroid analog of edge connectivity and the edge version of Menger's theorem?
no, not that I know of. But actually, when I say not that I know of, that's all I can say. But the natural connectivity for matroids, just when you do it and you look at what it means for graphs, it just naturally generalises vertex connectivity.
The reason I'm asking is Menger's theorem, I like to think of as a special case of the Maxwell mean cut theorem,
Sure.
where you have edge or vertex weights.
Yeah.
Can But that doesn't seem natural in the matroid context.
No, I don't think
Wait.
so. No, I've never thought so, but it might just be because I haven't ever looked at it in the right way. Yeah. All right, so just a few facts about. So so Menger's theorem for matroids genuinely generalises Menger's theorem for graphs, and the proof is easy, and that's a sort of and so it's nice. So it's often if you see versions of there are some very elegant proofs of Menger's theorem for graphs, but there are also some extraordinarily inelegant proofs of Menger's theorem for graphs, and they're inelegant because you don't really need to worry about keeping track of vertices and disjoint paths. All you need to worry about is, just keeping the right connectivity. And I mean, you can mimic that proof in graphs. It's quite an easy proof. Anyhow, better move on. Just sort of a bit of terminology here. A matroid is k-connected if there are no non-trivial k separations, or less than or equal to k separations, I should say. So, that's just... So obviously you can get some trivial separations because the cardinality of the set is small. So you just avoid those trivial ones. In particular, a matroid is not connected if there is a zero separation. And as Alan pointed out before, in those graphs G1 and G2 there, the matroids of those two graphs are the same. Matroid can't tell when things are, when you've got a cut vertex. As far as the matroid is concerned, it thinks of those two triangles there as being separate components. So matroid connectivity doesn't generalise. Disconnected graphs and one-connected graphs are all the same as far as matroids are concerned. But once you get to two connectivity, it all corresponds. So a graph is two connected if and only if the matroid is two connected, and the graph is three connected if and only if the matroid is three connected, up to parallel edges. That's just a slight little thing that you can have parallel edges in the graph, but that's not a big deal.
Jeff?
Yeah.
If you could get back vertex connectedness by taking the graph, add a new vertex, and then add an edge from the new, take the cone and add an edge from the new vertex to each of the old vertices, and then consider the matroid of that.
Well,
You distinguish between connectedness and unconnectedness by doing that.
Yeah.
Oh yeah, no, actually that's a point. If you do want to have a setup, for example, you could distinguish trees by actually, I mean there are various tricks for doing exactly that. So if you did want to matroidally distinguish those sort of structures, you could do it by making the graph somehow richer and getting a bit of connectivity. You can do that, and in fact it's a useful trick to apply at times too. All right. This just another observation. So we have two connected matroids and three connected matroids. You want to think of these as generalising two connected graphs and three connected graphs. That's what I'm saying. Bill talked about the decomposition of two connected graphs into three connected pieces. That decomposition extends to matroids, and that was done by Bill, but a different Bill Cunning. Well, the original. I was trying to be smart here, and it's silly. It's a real sort of nerdy mathematician way of being smart, because the original decomposition was done by Bill Tutt, and it was spoken. Bill Jackson talked about it and was extended to matroids by Bill Cunningham. But if Jack Edmonds were here, he'd kill me because I mentioned his name before Jackson. but actually, I shouldn't have said that. Okay. So, but what that means is that in fact you can decompose into three connected pieces, and often that means for a lot of matroid problems, it often means that it often suffices to just look at three connected matroids. That's really the point. That a nice sort of fact. All right. What I want to do now is sort of talk about a bit of classical matroid theory to give you an idea of what I think the good mathematics in structural matroid theory goes. So I want to talk about sort of one of the most famous chapters in the history of matroid theory, regular matroids. Now, a matrix over the rationals is totally unimodular if all of its subdeterminants are in 0, plus or minus 1. Now, totally unimodular matrices just plain arise in lots and lots of situations. But in particular, they arose in combinatorial optimization. And the observation is that a lot of problems, well, a lot of integer programming problems, for example, I think an integer programming problem is, I don't know enough, can be easy if the matrix is totally unimodular, and because the optimal solutions for the linear programming problem will always be integral. There's a sort of, you get that. So the point is that totally unimodular matrices have very, very nice properties, and you'd like to be able to recognise when a matrix is totally unimodular. But if I just give you a 0 plus or minus 1 matrix, well, it's a potentially exponential search to decide if it's totally unimodular, because you've got to check all the subdeterminants to see whether or not you don't get thrown out of that. So the thing is that, okay, once we've got a matrix, we can talk about a matroid associated with the matrix. And a matroid M is regular if it can be represented by a totally unimodular matrix.
And here you mean represented over the rational.
Represented over the rationals, yeah. I mean, I'm defining total unimodular over the rationals anyhow. Yeah, yeah. So, and of course there are some easy facts about regular matroids. They're minor closed, you know, you just have to check that these properties hold. So it gives you a nice minor closed class of matroids. So one way of thinking about the question of recognising a totally unimodular matrix is to whether a question of recognising when a matroid is regular. Similar, it's essentially the same question. What are some examples? So I just want to make the point, I really think that this is a class of matrices that rise naturally in lots of situations. Nothing, you know, people that aren't interested in matroids at all can still be interested in totally unimodular matroids. And the question of recognising total unimodularity is a genuinely interesting algorithmic problem. There are some famous examples of totally unimodular matroids. Graphic matroids are easily seen to be totally unimodular, and I gave you a totally unimodular representation of a graph last time, and that representation is always totally unimodular, a sort of exercise you can do with any class. Co-graphic matroids, because the dual of a regular matroid is regular, or you just do the exercise of finding the dual, and that's true. The matroid R10, and there's a representation of this. I cheated there, because that's a binary representation of R10, and you've got to be able to apply pluses and minuses to those ones in a way, and it works, but I've forgotten, but there's some 10 element matroid. That's all you need to know, and it's not graphic or co-graphic, and it's highly connected, right? So it's sort of a certificate that not everything, these aren't the only things. So that they're examples of regular matroids. So the class of regular matroids, and here's a theorem that I just think is, when it's all packaged together, is just plain a very beautiful theorem, and it's again a classic theorem of Tutt's. Goes back to the 1950s. It says these things are equivalent. So here we've got, so what are we saying? Here's a class of matroids, and we'd like to understand more about this class. When you get the class given to you somehow, it's just given to you by matrices with these properties. Well, you look at it and what do you see? Nothing really, it's sort of amorphous. But here we're starting to find out a lot more about this class. So Tutt said the following are equivalent. First of all, the class of regular matroids is precisely the class of matroids that are representable over every field. Now I mentioned yesterday that graphic matroids are representable over any field you like. And regular matroids, it's not hard to do, regular matroids straightforwardly seem to be representable over any field you like. The converse is the interesting direction. Just because I give you a class of matroids that's representable over all fields, it's the reverse direction that's the tricky direction, right? That if you're representable over all fields, then you must be regular, that you've actually got the full class. Anyhow, so there's a sort of a connection between a purely algebraic thing, total unimodularity that you just say, and here's somehow some question about representability over different fields.
The easy part of that, what you actually show is you take any totally unimodular matrix over the rationals that represents M,
and then just
interpret it in F, it will represent the same matroid over F.
Yeah, and there's just sort of, actually there's a sort of an algebraic way of observing that there's just a homomorphism sort of from these things. It really is genuinely easy. It's the reverse direction that's not so easy. And the other thing is that here's another excluded minor characterisation. It's a minor closed class. Oh, by the way, the third one is that it's interesting that being representable over all fields is the same as being representable over GF2 and some field of characteristic not 2. That's enough, you know, that pair of fields does it for you. The rest of the fields, that's a sort of a basis for that sort of space in something. And the last thing here is, and this is the more difficult thing, improving this, but that M has no minor isomorphic to the 4-point line. F7, remember, that's the Fano, that's the binary projective plane. And the dual of the binary projective plane, it's a matroid. And so that's an excluded minor characterisation. Well, now you started to understand a lot more about regular matroids, or totally unimodular matrices, right? You can see that they correspond to natural classes. But the person comes up to you, this is the tragic thing, you know, you've done this really beautiful mathematics, and also this represents fantastic insight from Tut's point of view, because he did this in the 1950s. In the 1950s, why would you think of doing this? I have no idea, you know. There was no models for seeing this as the way to go. Why would you think of looking for these types of characterizations? But it's very beautiful in that, but tragically the combinatorial optimizer comes and tells you, yeah, but how do I recognize a totally unimodular matrix? And you say, oh, well, I've got this really nice theorem here, but it doesn't help you one little bit. So so when you have that, what do? You bring in the bulldozers, and if you want someone to drive a mathematical bulldozer for you, you just ring up Paul Seymour, right? And he says, well, who cares about beauty? Let's just sort of... Actually, that's not true. This is a genuinely very beautiful theorem, but Paul is not afraid of technicalities or not afraid of doing what he has to do to get the result. So what you want... So what we've got is a very nice, attractive theorem about regular matroids, but it doesn't tell us anything algorithmically. So now what Paul does is he gave an explicit structural characterization of regular matroids in terms of more fundamental subclasses. And if you want to understand essentially the strategy behind 90% of the theorems that Robertson, Seymour and Thomas have done over the years that have knocked over big conjectures, that's what they do. They give structural characterizations of the class involved, and then they say, oh, okay, to answer your question, let's just take a photograph of the structure and see what it looks like. That's their strategy. And it's an incredibly powerful strategy. I mean, that's how they solved the perfect graph conjecture. They just gave their structural characterization. And that's how they do the well-quasi, the graph-minus theorem. This is for those of you who know about this stuff. The graph-minus theorem, the well-quasi-ordering result, comes from a qualitative structural characterization of the class of graphs with no fixed clique as a minor. Extraordinarily powerful, and Paul himself will say that this is the first theorem he ever did which used that type of strategy. So what you observe is, here are some operations that preserve regularity. Direct sums, that's an operation that you can do for matroids. That's the reverse of splitting across a separation, right? You just take the direct sum of two matroids. Two sums, so if just that's an analogue of taking a two sum of graphs, right? You just you take this all works. These all work. Two sums work for an arbitrary matroid. You just take this matroid, you find a point, you identify it, and give in such a way that you get a two separation, and you may or may not delete the point. It's up to you. And if you do it along a line, which makes sense in binary matroids but not in general matroids, if you do it along a line, then you get a thing called a three-sum.
Do three sums make sense only for binary?
They make sense for other classes of matroids, but they only easily make sense for binary matroids, and they don't. For non-representable matroids, for example, they don't sit. But for any class of representable matroids, I can give you an analogue of three sums. But yeah. But it's quite straightforward for binary matroids. In some sense, it's just an analogue of clique sum along a triangle, and so quite easy to see. These properties preserve regularity. And notice using this, you could start off with a big graphic thing and a big co-graphic thing and a bunch of stuff like you could find do these operations, you end up with some tree-like structure. But it's far from being graphic or co-graphic. So there's lots of regular matroids that are neither graphic nor co-graphic. But Paul Seymour's theorem says that really graphic and co-graphic are the fundamental classes of regular matroids. If I give you a regular matroid, then that matroid can be built by starting off with graphic and co-graphic matroids and doing these elementary composition operations. Or if I'd say it in the reverse, and copies of R10. Remember R10 was that little 10-element matroid? Well, it was very clever of me to just choose that particular example, but there I did. So So that's just the one slightly bizarre matroid, but apart from that, if you're it also says if you're highly connected and regular, then you are graphic or co-graphic, right? Because otherwise you've got a low order separation and you can split it apart across these low order separations. And that's an extraordinarily powerful theorem, and it just tells you this is what a regular matroid looks like if you're prepared to believe that graphic and co-graphic matroids are somehow fundamental classes. And of course, if you can reduce your problem to graph theory, if you can reduce a matroidal problem to a graph problem, you're typically pretty happy, right? So because you've got a description in a class that's somewhat simpler. And that leads to a polynomial time recognition algorithm for totally unimodular matrices. And it says if I give you any matroid, doesn't have to be, just give you any matroid, it's a polynomial time recognition algorithm for, and how does it work? Well, you can find 2 separations and 3 separations in polynomial time. That's long been known. So you just decompose until you no longer have any more significant 2 separations or 3 separations. And then you look at that thing and then proved that you could recognise whether or not a matroid was graphic in polynomial time. And essentially that's how the algorithm goes. So Seymour's theorem is a very, very powerful theorem, and possibly a wonderful theorem. So there was Alan mentioned in the last talk about the complexity for matroids. So I want to say a little bit about that. So when I said that you can recognise whether or not a matroid is regular in polynomial time, that's pretty straightforward. What I mean by that, if the matroid is given by a matrix. The issue is how am I given the matrix? How am I given the matroid? If I give you the matroid as a matrix, well, then it's clear what the size of the input is.
Over some arbitrary field.
Over some field, right? You've got this description, and then it's just a normal sort, and then that's just a normal question with normal things on the size of the input, because you've just got this combinatorial object that gives you a matroid. But what if I just say you've got this matroid M? Well, a typical matroid doesn't have a nice description like that. It just it'll have n elements, but exponentially many bases. And however you describe a matroid, the typical way of describing, you're forced to have this exponential description in the size of the set of elements. So what sort of model of complexity would make sense for that? Because if we just say, oh, well, the size of the matroid should be the number of bases, that seems extraordinarily indulgent. You just, because that's not a natural thing, and it doesn't correspond to what you would have, you wouldn't, if the matroid were given to you by a graph, you wouldn't think of it being natural to measure the size of the input as being the number of spanning trees, right? You're getting a lot for free there, I feel. So there are no free lunches. So what we'll do is we'll say the size of the input is the number of elements. And we'll say we've got an oracle. And so what you want to do is you've got a polynomial time algorithm for things. If you are allowed to ask this oracle tells you ask the oracle, is this set independent? So it's an independent set oracle. And it'll tell you yes or no, whether or not it's independent. We're not saying how you decide whether or not it's independent. You can just assume essentially you're saying that you've got a subroutine that decides whether or not a set's independent.
The oracle charges 1.
Yeah.
It's a polynomial algorithm. You need to.
The oracle charges 1. Yeah, exactly. And so that constitutes one step, and that makes sense for all sort of reasonable models where the matroids are given to you by a graph or a matrix. The oracle essentially charges you something like that. So that's and so when I said that the Robertson-Seymour that Seymour's theorem leads to a polynomial time algorithm for determining whether a matroid is regular, that's with respect to that model. Well, you can ask other questions and say, oh, okay, I can decide whether or not a matroid is regular in polynomial time. Can I decide whether a matroid is binary in polynomial time? Here, that you would think, that's not, how hard can that be? We already saw that deciding whether or not a matroid is binary matroids have a unique excluded minor, it's the 4-point line. So all you've got to do is decide whether the matroid has the 4-point line as a minor or not. That doesn't seem like rocket science. Well, in fact it is, because it's, well, actually, I don't think that rocket science is rocket science. I mean, it's just an application of Newton's third law, but there you go. It's, but then again, I'm not a physicist, so how would I know? So, okay, so that the point is, with respect to the Oracle complexity model, deciding whether a matroid is binary is provably exponential.
That's even worse than being NP hard.
Oh, it's as bad as it could be. So, and not only is it provably exponential, I'm essentially going to prove it to you now. And it's a nice. So, what that array of lines is meant to be is, so imagine I'm in a projective space, binary projective space. Now, in a binary projective space, I've got lines. All of the lines have exactly 3 points. These points around here, I'll take to be a circuit, right? And these points, and then I'll take another point there. Now, so what I'm effectively, another point, so what do I mean? It's a set, I mean, it's easy to see that you can do this. This is a set of points in the binary projective space that's independent. So this has got high rank, this thing, even though it just looks like it's on the plane. This has got very high rank. So this is a set that's independent, has the property that when I delete any one of these points, I become independent.
Actually, it's dependent.
It's dependent, but so think of this set of points as a set of points representing the matroid of a cycle, right, of a single cycle.
So these spikes, you should think of them as in generic position in high dimension, except there's one more dependence. Right
But now well, not quite, right? I'm just saying I'm actually describing the spike.
The outer points are...
They form, these outer points are, they're like the matroid of a cycle. So they have the property that they're not independent, but every proper subset is independent. And I can do that in binary space because that's just the matroid of the graph of a cycle, and we know the matroid of the graph of a cycle is binary. So I can get that in binary space, and this point here, which I haven't drawn in, is just some point that's not in the span of that set, right? So I've got this set of points here that are almost independent but not quite, right? And this is a point not in the span, and then this is the other point in binary space that's not on that line, right? So and there you go. I've given that thing, and it turns out to be for each rank R, there's one of these. I can just construct it. Someone had their hand up, was it here?
Yeah. So in 3 space, if I want to visualize this in 3 space, there'd be 4 lines meeting at the apex.
Yeah. Well, on the plane, I'll do one for you on the plane. On the plane, my 3 points form a cycle, so that I've chosen that. And my other point would be that. And then what I'm doing, so this point's not actually in my matroid. And then, so now there's exactly one binary point there, and one binary point there, and one binary point there. Now if I say, oh, well, this is all binary, when you look around and say, oh, there's a lot of other dependencies kicking around, right? And there are. In binary space, there's got to be, I mean, because, you know, I've got 7 points. Well, if I've got 7 points there, I've got to have the full rank 3 binary space. So I've got, and there are dependencies that just happen when you choose these points here. So this looks as if I'm putting these points freely on these lines, but it's not happening because you can't do that because you're in this very highly constrained binary space.
So point X is not in the matroid.
Point X is not in the
But
matroid.
it could be added.
I could add it if I want. Yep,
Okay.
Yep. It
And
just leads to a simpler description if I throw it away at the end.
Okay, and then the points in the middle are placed freely on each point in the middle is placed freely.
No, because in the binary space, I'm doing this in binary space. So if I look at the line joining this point and this point, there's only one other point on it.
Oh, okay.
So there's no freedom here. I've just got to take the one that's there,
Okay.
right? And so in binary projective space, there's 3 points on a line. So I'm doing this in projective space, but given there's only 3 points on any line, that last point is determined. It's anything but free, interestingly enough, yeah.
You know it's not on the circle.
Yep. I do, because the span of this stuff here, this is a circuit. I do, because this point here is chosen to be not in the span of that, and if this were on the span of that, then I would pick up that point in the span as well, right?
So this is one fixed construction.
This is a fixed construction. Yeah, yeah. And now this is a binary matroid, right? And now I'm going to tell you a few facts about the binary matroid. I'm going to tell you some things about the circuits. Remember, the circuits are the minimal dependent set. Well, there's a lot of 4-element circuits there. These are things like this. And the other circuits, there's an exponential number of other circuits. And the other circuits are certain transversals of these lines, right? So, for example, in this example here, there's another circuit. But not all transversals of those lines are circuits. There's a transversal of the lines. Here are my lines. There's a transversal of the line. That's not a circuit. But in any case, there are exponentially many transversals of those lines that form a circuit. That's easy to see in binary space. You just think it's just easy to see. Now, there's a trick that I can do. Because these circuits are actually very large circuits, I can take any one of those circuits and declare it to be an independent set. If I do that, the matroid will no longer be binary. If I do that, the matroid will no longer be binary. It'll still be a well-defined matroid, just changing that single circuit to an independent set. That's all I've done. It'll still be. Now, you have to decide whether I'm the oracle. You've got to decide whether I've got the binary matroid in mind or the one obtained by just taking one of these circuits and declaring it to be independent in mind. Well, I'm going to tell you, you've got to ask me an exponential number of questions, and I can tell you, when you've asked me a lot of questions, you've still asked the wrong question, right? And so that's a proof that it's exponential, and there's something nice in complexity to actually be able to say, look, I can prove something's genuinely hard. Gordon.
Does that mean the rank function is identical everywhere except for that one point?
No, not really. No, but it's the nice way to think about it is if you do it with respect to a basis oracle. If it's exponential with respect to one oracle, it's typically exponential with respect to others. So assume I've got a basis oracle, and then then you've got to decide. So these sets are either bases or circuits, right? So the rank can be.
Can there be a difference in complexity depending on whether you have an independence oracle, a basis oracle, or rank function?
There are subtle differences. Yeah, there can be things that are hard with respect to one of these oracles. But actually, if I'd say any more, I'd be sort of because I've forgotten. but I knew something I knew about once. But typically, this problem is very robust under the choice of oracle. This is an example given by Paul Seymour. So on the one hand, we have recognising regular matroids is easy, and recognising binary matroids is surprisingly hard, you know. And that actually makes Seymour's theorem for recognising regular matroids even more impressive, right? Because you've got this thing that's hard. And of course, it's not hard. I mean, once you see this example, it's good exercise to say, can I generate similar examples for other fields? And of course you can. So that deciding representability over any fixed field is a genuinely difficult question. Now at this stage, in my original preparation, I was going to talk a bit about the Tutt polynomial for matrix, but then I decided, well, not really, there's no point, because, I mean, Alan talked about Tutt polynomials and how they were matroidal and things like that, so what I did was I sort of changed my mind, and I thought something quite different is making a pitch for some results of mine. You know, that's always a good thing to do, and it's sort of the question is, so this is something that obsessed me. Well, this is good. These are results of mine that go back probably about 12 or 13 years now, but that was something that obsessed me at the time is what we were seeing with regular matroids. Was that typical behaviour, or was that a regular matroid a very, very special class? And I thought, well, the interesting thing to do would be, so we know that regular matroids are precisely the matroids that are representable over, say, GF2 and some other field of characteristic not 2. So they're the class of matroids that you get when you look at a pair of fields or a set of fields and ask for the matroids representable over that set of fields. And I thought, well, do we have nice answers for that question for other fields? And so I thought, well, the natural field to look at is GF11. No, I lie, it was GF3, the 3-element field. And it turns out that there are some genuinely nice answers to these questions for the 3-element field. So I just want to sort of point out that what you were seeing was regular matroids, at least at one level, at the level of attractive theorems but not satisfactory algorithmics. There really genuinely is a similar sort of structure for other classes. So here's a class of matrices. I mean, you can just define a class of matrices, right? Here's a class of matroids that we can define, call them dyadic, and they're matrices over Q with over the rationals, or I could have made it over the reals or anything. But where all the subdeterminants are 0 plus or minus 2 to the power k, where k is an integer, right? So you can have a half and stuff like that. That's a generalisation of regular, right? Because plus or minus 1, I can take powers of plus or minus 1, but plus or minus 2 to the k gives us something genuinely different. I'll call a matroid dyadic if it can be represented by such a matrix. Again, there's an easy question, easy direction here. It's easy to prove that if you are dyadic, then you're representable over GF3 and GF5. Right? That's an easy direction. The hard direction, at least I found it very, very hard, but I eventually did it, is that the converse is true. If you're representable over GF3 and GF5, if you take a matron, I give you the 3, and you're representable over the 3-element field and the 5-element field, then you must be dyadic. That's exactly the class, and that's an analogue. So it's quite a nice generalisation, not a generalisation, an analogue of the regular matroid thing. It's also true that being representable over GF3 and the rationals is the same class. So which ternary matroids can I also represent over the rationals is the sort of, and that's of course that's an interesting thing that. So that's a start. Remember, for regular matroids we had those nice results of Tuts, and then we had the wonderful result of Seymour's. Well, here this is part of the nice result of Tuts, right? We've got this characterisation of this matrix class in terms of representability over a certain set of fields. We don't have the rest. We don't have an excluded minor characterisation for this class, and we don't have a structure theorem for this class. And we don't know about polynomial time recognition for this class. These are all entirely open questions. And I think genuinely very interesting questions. Are there any other classes? Well, with binary, we really only saw one class. You're either, you're just regular. If you're representable over GF2 in some other field, then you're regular. But it's more complicated for ternary matroids, and there are other classes kicking around. There's a class that I called 6th root of unity matroids, and much to my disgust, they should have been called complex unimodular matroids, because Alan and... is that in the long paper of yours?
Yeah. Long paper with
yeah.
Huxley.
I'd prefer these to be called complex unimodular now, but I defined this class to be the class of matroids that you take the matrices that you can represent over the complex numbers, where all subdeterminants, non-zero subdeterminants, are 6th roots of unity, right? Because that's fine. Nothing wrong with that. But in that paper that Alan, they observed, and the frustrating thing is the proof is not difficult, they observed that this class is actually the class that can be defined in a much more simple way. You just say, look at the class of matrices representable over the complex numbers, where all subdeterminants have complex modulus 1. And that's a totally natural generalisation of regularity for complex matrices, right?
Modulus 1 or modulus 1 or 0.
Yeah. All non-zero, yeah, exactly. That's so, that really bugged me when but it's a nice answer, and I don't know if you still call them 6th root of unity matroids, but complex unimodular is a much nicer name for them now. And it just turns out that what it means is if you get one of these matrices, you can transform it into a matrix by some straightforward row operations and scaling to where all the subdeterminants are 6th root of unity. So you only need the 6th root of unity. Anyhow, that's a class of matroids that gives you a class of matroids. And these turn out to be exactly the class of matroids representable over GF3 and GF4. And also you can say things like this. You can say that a matroid is representable over GF3 in the complex numbers, if and only if it's either a 6th root of unity matroid or a dyadic matroid, or can be obtained by 6th root of unity and dyadic matroids by taking direct sums and 2 sums. So there's a sort of anyhow, this there is an excluded minor characterisation for this, and the reason is because there's an excluded minor characterisation for this class and an excluded minor characterisation for this class. So you get the excluded minor characterisation from that. But there's no structure theorem known for that. There is another class that I don't really want to get into, another interesting ternary class too, which is the class of almost regular matroids. It's just slightly technical, more technical to define. But that's the class of that turns out to be the class of matroids representable over GF3 in all bigger fields. So as opposed to binary matroids, if you start to look at what sort of are the analogous classes to regular matroids, you get them, but the number of classes starts to become more complex. But the answers are beautiful. I mean, I think that these are natural classes, and I think it's just nice mathematics when you ask a question about here's an intersection of two classes of matroids, and at least they turn out to correspond to something quite attractive.
How many excluded minors do you have?
Oh, yeah, not many, sort of like 4 or 5. You just have to, there's sort of 5 or 6 excluded minors for GF4, and there's 3 or 4 for GF3, and I mean, so my head's too full to it. I can, but it's not many, it's straightforward. Yeah.
So the order might match,
Yeah.
So there is a huge difference between the definition of a regular matroid and your definition of this dyadic matroid, and I don't think that you should expect ever to have a structure theorem, or maybe some miracle, but there is a huge gap. Let me tell you why. If you have a regular matroid, you don't play with geometry, because you are over the lattice of the integers, and every basis, let's say that you have an integer matroid, not a rational matroid, and every basis is a basis for your lattice with integer summation and so on. That's the total unimodularity.
Yeah.
But when you go to your definition, the only thing that you know is the determinant. So you know that you have some sublattice of a certain index that your vector span, but you don't know what this sublattice is. You don't have a handle on the geometry.
Well, but
now I can play with all these sublattices around that they don't interact in any way, and you want a structure theorem on such.
I believe that a structure theorem exists, nonetheless. But the thing is, I'll happy to talk about it a little bit later, but there is a natural, you see, what you've got to do is you say, what is the analogue for graphic matroids for this class? And there is an analogue for graphic matroids for dyadic classes, and they're the matroids, the biased matroids of sign graphs, which the theory of which Tom developed. And maybe because I'm not actually looking for a structure that decomposes into graphic matroids and duals of graphic matroids, but I would look for a structure theorem that decomposes into these classes, which are not as simple. Maybe that might help in that task, but I don't know. But I just want to sort of, just 1 or 2 more quick things that I want to say at the end. Here's a theorem that I want to pitch that's not mine, but I wish it was. And this is the theorem of Dirk Vertigen's, which he never published. Dirk Vertigen, I don't know how many of you know Dirk, but he proved a lot of lovely theorems in matroids, but he had a problem with writing up. He solved this problem by marrying a ring theorist. So now he works in ring theory. So anyhow, I think this is right. The roots of x squared minus x minus, this are golden means, right, aren't they? Is that the right polynomial? I think it's probably right. Okay, so I can look at the matrices over the reals, and I can say I want the matrices with the property that all subdeterminants and all non-zero subdeterminants are powers of products of. I'm not sure if that's exactly right, but essentially they're golden mean type powers of golden mean, and most of these powers are what. Anyhow, that's the class. Essentially, things look like golden means, and so there's a class that you can look at. It's matrices over the reals, blah, blah, and gives you a class of matroids. Well, Dirk Vertigen proved that that's exactly the class of matroids that's representable over both the 4-element field and the 5-element field. I just think that is, I know the proof, so somehow I can say it doesn't surprise me in the sense that the logic is inexorable, but in advance I would never, ever, ever have guessed that a result. So I believe that what I've shown you is the tip of an iceberg of what could be a wonderful, quite broad theory that whenever I do look at a set of fields, there should be other lovely sort of theorems that are just sort of pure sort of navel-gazing sort of mathematics in some sense, because I can't figure why you would care about most of these classes. Some of the classes arise naturally in lots of other situations, but why you would care. But nonetheless, I think it could lead to some. I think there's a lot of beautiful undiscovered mathematics in the area. Okay, that's the very last thing I do want to say a little bit about.
Excuse me, also, why, to me the most amazing thing is why would anyone start considering this class of matrices with these determinants?
Oh, you don't do that. You sort of do the converse.
Okay.
You actually discover, right? You find that there's a natural class. It's an interesting, it's a good question, right? But you just discover, and that you look at the techniques for solving these sorts of problems are reasonably, they're not trivial, right? But you end up, lo and behold, you get a bunch of constraints, and for what it means to be representable over both GF3 and say GF4 and GF5. And lo and behold, there's a unique type of matroid that satisfies those constraints, and that's that. So that's the way that's the direction one goes. Okay, so the last thing I want to say is it's just on a somewhat different topic, but I think because there is discussion about chromatic polynomials and to generalizations of matroids, I just want to say one thing that some of you may not be aware of, which I think is just a wonderful fact too. So I'm cherry picking here about stuff that I really like. But anyhow, so just as we're already aware that the Tutt polynomial can be defined for matroids, and the definition for matroids is just exactly straightforward, and it's just a direct generalisation. We can also define the chromatic polynomial of a matroid, and exactly you can define it either by a deletion or contraction recurrence, whatever your favourite way of defining, so long as you don't define it as in terms of K colorings or whatever. But there is a polynomial associated with a matroid, and it's an evaluation of the Tutt polynomial essentially. If you take the matroid of a graph, it's essentially the chromatic polynomial of the graph, except the chromatic polynomial of the graph has extra factors of lambda in the front but it's so up to that multiplicative factor, it's the same. The chromatic polynomial of the dual of the matroid of a graph, right? So that's a matroid. We can take its chromatic polynomial. That's the flow polynomial of the graph, and that's Alan talked about that. So actually both chromatic polynomials and flow polynomials are just both examples of chromatic polynomials of matroids. And that's what matroid duality does for you. So here's a theorem that Crapo and Roeder proved some time ago. And this is not the full theorem, but this is a version of it that sort of avoids as many technicalities as possible. If I give you a GFQ represented matroid, right? I'll give you a matroid that's GFQ representable, and then I just take some set of vectors that represents it. And so that means that there's some set of vectors A. And then I say, all right, what I'm going to do is look for the maximum corank of a subspace that avoids all of the points in A, right? I'll look for the maximum rank, but I'll index it by the corank, right? So I'm looking for the biggest subspace that I can find that doesn't contain any elements of my matroid. Then that subspace has, the corank of that, the difference between the rank and the rank of the full space that I'm in, is the same as the minimum value of K for which the chromatic polynomial is greater than 0. So that's just a purely geometric thing. If I want to know what that corank is, then that's the minimum value of K such that the chromatic polynomial of the matroid is positive. So what's that mean? Well, if it's the matroid of a graph, and then if it's the matroid of a graph, then the graph is four-colorable if and only if, when I represent the matroid of a graph as a set of points in binary space, if and only if I represent the graph as a set of points in binary space, I can find a subspace of rank R-2, so it's a coline, right? Subspace of rank R-2 that doesn't contain any elements of that matroid. And that's a purely geometric way of stating what it means for a graph to be four-colorable. Or here's a way of stating the 5-flow conjecture, right? this will simplify. If you want to work on the 5-flow conjecture, don't do it like this, but it's true. If I want to solve the 5-flow conjecture, so what that means is give me a graph, take the matroid of the graph, dualize it, represent it over GF5, and the 5-flow conjecture will be true if whenever the graph has to be loopless, but that means no, I shouldn't have said that, that's a distraction. When I represent it over GF5, there's a hyperplane of the substance that avoids it. So that means it's affine, because the chromatic polynomial at 5, so that's 5 to the 1, has to be greater than 0. Yeah, and that's it.
Shouldn't more be true? I mean, you say maximum k that something exists.
Oh, there's a lot more that's true.
But what I mean is the chromatic polynomial is supposed to count things.
Yeah, but that
Shouldn't it be true that the chromatic polynomial at q to the k counts the number
counts
of
the number of
subspaces?
k tuples of linear functions whose intersection avoids the thing. It really does count something, and the only reason and the much nicer way to state that theorem is to do the counting version, but I knew I'd be running out of time, so I just wanted to give a version where I could just make it clear that these problems for graphs are actually special cases of this very, very general problem of finding the maximum size subspace in a projective space that avoids a given set of points. And that's called the critical problem, for what it's worth.
With the difference that the chromatic polynomial for a graph counts something at every positive integer, whereas here it counts something at powers of a particular...
Yeah. And then there's a whole lot of interesting questions. Is if I give you, say, G of Q representable matroids, then typically you know that you're counting something at every power of Q. And for example, you'll know you'll be 0 at increasing powers of Q, and then once you become positive, you'll stay positive forever, for example, and all of that sort of stuff. What do you know about the chromatic polynomial of matroids in general for things that aren't? I think all sorts of weird stuff happens, yeah. But if it's a matroid of a graph, weird stuff doesn't happen because of what you've said. Yeah.
Isn't that, this is why I'm looking at this, isn't that minimum instead of maximum?
Probably.
Yeah, because it depends on what you're...
I've probably got something the wrong way around there, yeah.
Yeah.
I'm just not very good at that.
See, I was trying to figure this out 2 days ago.
Yeah. I mean, I know what I mean. I just can't write it down, that's right.
I think it's a maximum subspace, so it's a minimum codimension.
Yeah, that's right. You see, I had minimum there. Yeah. You're looking for the biggest subspace. Right. And when you found the biggest subspace, the thing that you measure, you're exactly right. Yeah, you measure the codimension, and then, of course, that will minimise the codimension. Yeah, no, sorry. So Tom's exactly right. Yeah.
So if you go back to the same old characterization theorem, these 2 sums and 3 sums, do they correspond to matrix operations that are sort of recognizable if you want to go backwards? If you're given a matrix, you want to recognize whether...
Yeah, they correspond to sort of ways of... it's a straightforward sort of linear algebra, but I mean, a 2-sum will mean that I'll have a partition. This is up to sort of doing some row operations, which you can always do, where these will be zeros and got arbitrary stuff there. Well, maybe, I always get confused about this, but maybe I mean, because having a direct sum is just having a partition like that. But it might be that this has rank 1 there and rank 1 there, perhaps, right? But you have these very, very low... no, sorry. These might be rank 1 here. I mean, this is something that I know, but you know, I'm cracking under pressure. and you've got arbitrary stuff there and arbitrary stuff there, and somehow I feel that there's a sort of a row and a column.
In those corners, but there's that overlapping lines.
Right. The top left
Right.
Top left is one matroid, the bottom right is the
Yeah,
other matroid.
but you have these overlapping lines or something like that, so it's not exactly a partition. And the same, that's a 2-sum. So you can recognise, and the thing, if you give me a matrix, there are good algorithms for finding a 2 separation too.
So there's sort of a canonical decomposition that comes in, right? On the matrix, if you're given a matrix.
Yeah, there is a canonical decomposition, but actually finding the canonical decomposition sort of is not. I mean, it's doable and it's done, and I think there's a nice paper in the thing of combinatorics, that big blue book by Bill Cunningham, and I think that shows you these algorithms. But of course, there are issues, and these are exactly the same issues that turn up in finding the two-sum decomposition for a graph if you want to get this canonical.
So this canonical decomposition is the matroid analog of the decomposition that Bill showed.
That's for two sums, but there actually for three sums there's not a canonical decomposition for three sums.
But nevertheless, there's
But
an
it
algorithm
doesn't matter
protecting
because
them.
what you do is you take an arbitrary decomposition. You find a three separation, you decompose, and you do it all. It's not canonical. All you have to do is record what you've done, right? And then you can rebuild the original matrix. It's sort of like a dynamic programming sort of algorithm, I suppose. But, well, for the decision problem to decide whether or not the matroid is regular, you don't even have to record what you've done. You just do it all, and then till you can't do it anymore, and then you run the algorithm on the bits. And you can forget about what you've done, because you just have to decide whether the bits are graphic or co-graphic. I think that's right, yeah. Yeah.
Is this characterization problem for matrices of these different types, does it become any easier if you drop the zero condition and just assume?
No, because you see, so like the thing about it is that the zero condition will inevitably arise. You'll inevitably have some subdeterminants being zero. You'll inevitably just simply because otherwise the matroid itself would have no dependent sets. See, I mean, once you've got a dependent set, you're forced to have some subdeterminant being zero.
Well, okay, maybe I meant to say then I'm thinking of a different problem where you would say look at maximal minors. Because there you can, I mean, I'm thinking an analogy with total positivity where if you look at maximal minors of a k by n matrix.
Well, there might be something that's true that when I say you have to do this search for all subdeterminants, you might be able to say I can find a somewhat more restricted set of subdeterminants that I can look at, and if the property holds for that restricted set, it must hold for all of them.
But
And
if
I
all the
don't
maximal minors are non-zero, then the matroid is uniform.
Right. So that's which means it has no non-trivial, no small dependent sets. Which yeah. Bill.
Well, it's really an answer to Alan's question about an analog for edge connectivity. So the direct analog in the cycle matroid of a graph would be to find the minimum core circuit. So if we took that as a measure of the thing that corresponded to edge connectivity in a matroid, then it's not so good because it's NP hard to find the size of a minimum core circuit in a matroid. But there are, and you'd also want a Menger theorem, so you'd want something like the size of a smallest core circuit that contains an element is equal to the maximum number of disjoint circuits that contain it. The disjoint apart from containing the element, and that there are families of matroids which satisfy this property, but most matroids don't. But I think regular matroids would.
Well, yeah, and actually you may expect such a thing because of CMOS decomposition theorem.
That's what I thought it might.
Yeah. Did you?
So, just to go back to the remark that I made before, so I think that your perception of a regular matroid is really that those determinants are plus minus 1 or 0, then I dismiss them. And this determinant condition can be tried to generalize to get structure, but an equivalent way to say what a regular matroid is to say that every basis spans over the integers the full lattice, right? The lattice of the integers. And now when you want to generalize, go and take sublattices, a string of sublattices of any type over the integer lattice, and say that every basis of your matroid is now span one of these sublattices. And let's see what you get the structure theorem. And you can reduce your setup with the case that these are specific lattices, and go and let's see whether you can get, you have now more structure. And if your conjecture is correct, you need to give me a structure theorem on this more special case when the lattices are pinned down.
Well, can I give you a structure theorem that's true for any proper, well, we believe it's true, and this is work I'm doing with Jim Gillen and Bert Gerrard, which is, we believe it's true, and we believe that we'll be able to prove it sometime this year. But we've been working on it for 8 years, so I mean, but we sort of think we're getting there. And it says something like this: that if I give you, for a prime field, this is, if I give you a proper minor closed class of matroids that are representable over GFP, then up to a bounded rank, I'll give you a very highly connected one, right? So now I'm not saying exactly what I mean by highly connected. All of these things are sort of got a state in an extremal sort of way, right? Give you a very highly connected thing. Then that up to a sort of some bounded sort of rank stuff. So like this means that I can add a bounded number of rows of junk essentially and things like that. But I've got a bounded number of ones. The matroids that I get are either matroids that I can associate with group valued graphs in the sort of way that Tom Zaslavsky developed, or they're duals. And we believe that we'll be able to prove that. Now the thing about it is I'm probably thinking about these questions in a very different way. I'm coming at these problems from a very, very different perspective than you're coming at them from. But what that means is that that's saying qualitatively every proper minor closed class of GFQ representable matroids does have a structure theorem. That structure might be very, very hard to find explicitly. And so what the regular matroid decomposition is an example of an explicit structure theorem. And that's really the matroid analogue that we are hoping to prove of the Robertson-Seymour structure theorem for graphs that says if you've got a proper minor closed class of graphs, then up to some bounded stuff, you really do look like graphs embedded on the surface of bounded genus. So we really believe that we can prove that there is in some sort of qualitative sense, there always will be a structure theorem for a proper minor closed class of, say, ternary matroids. Whether or not we can ever find that structure is another question altogether. I don't know. It's probably not answering. We're probably talking a bit at cross purposes there, but it's yeah. Okay, well, I think I'll